Thanks for the introduction, Xiaojun. Just a small, quick announcement. I will join Stony Brook Universities from January 2017. So this work I did with Shumin Zhai at Google. So selecting target with finger is probably the most important and fundamental task for touchscreen interaction. And one very core issue to this problem is how big targets should be. What's the appropriate size of a target? On the one hand, if the target should be big enough in order to accommodate the imprecision finger touch. On the other hand, if a target is too big, it takes too much screen space and it limits the number of targets you can shoot. So the designers need to strike a balance between the space and the accuracy of the target. And also, targets often come in different shapes. We need to find out what's the appropriate size so that can be easily selected by finger and can also fit in the layout of a given UI. And also, right now we have some interface is designed for both pen and touch. So we need to strike a balance between the two input modalities too. So all this comes down to deciding the appropriate size of finger of a target. And this research question actually has drawn a lot of attention from the designer communities. For example, in the Android design guideline, it actually suggests that the target should be at least 48 dp big in order to accommodate finger. And 48 dp is around 7.6 millimeter. So to decide the appropriate size of finger, so the appropriate size of target, the current approach is trial and error. So you basically just run a bunch of user studies and change the target size to see how the accuracy change. So the problem with this approach is that it's not scalable. So if you have a large range of target size and different shapes, does that mean that you have to run user studies of every possibility? And also, the results from this approach is how to be built on. For example, if you want to do UI optimization or automatic UI generation, it's how to use the results from these empirical studies. So in this research, we propose a model that will predict the accuracy of selecting targets with finger based on target size only. And our evaluation shows that this model, the prediction error of this model is less than 5% for most of the targets. And in the rest of the presentation, I will show you how we derive the model and how we evaluate it and what the model can do for us. Let's start from very basic target selection task. So here I show a vertical target here. And typically you will use land your finger to select it. If a touch point falls inside the target between the two boundaries, it's a success. Otherwise, it's an error. So, and it has been shown by previous research that the touch points distribution of this, the touch point distribution follow Gaussian distribution. So the probability density functions could be formally described in this formula here. And then, based on this formula, we can know that the success rate of selecting this target is equivalent to the probability that the touch point falls inside the target. And we can do the simple integration here. So it's an integral of the PDF from x1 to x2. This x1 and x2 are two boundaries of the target. And then we just put in the Gaussian distribution here. This is straightforward. And then if we assume that the center of this Gaussian distribution is a target center, we can further reduce the formula to this term here. And it can be seen it only have two variables. The first is W. W is the width for target. We can get it from the target task itself. And second variable here is the standard deviation of touch point distribution. So basically, this equation shows that if you want to know the accuracy of a selecting target, we need to know the size of a target and also know the standard deviation of the touch point distribution. So the very core question here is how do we estimate the standard deviation of a touch point distribution given a target size? And we did it by using a hypothesis which we call Dual Gaussian Distribution Model. Basically, it provides a method, a view to describe how the distribution of touch points is formed. So basically, it decomposes the procedure of selecting a target into two components or two steps. So basically, here I show a target, and to select it, the first step is that you will put your finger touch area, a contact area, on the target, and the location of this area follows a Gaussian distribution, with the center is the center of a target. This is the first step. You land on your contact area of finger touch. And the second step of this target selection procedure is that the contact area will be reduced to a single touch point. But where the touch point will be within this contact area, and we also assume that it's follow Gaussian distribution. So basically, it shows that, and the eventual distribution of touch points is the combination of its two components, two procedures. So the first component, we call it the XR. It's a relative component. It's basically where you place the contact area of the finger, and this component it's related to the target size. It basically shows you to what degree you will use the width for target. And second component here is we call it XA. It's a procedure where the contact area is reduced to a single touch point. And for this procedure, it's independent from the target width. We call it absolute component. It basically reflects the inherent ambiguity of finger touch. And based on these assumptions and these principles, the final distribution of touch points is the sum of these two Gaussian distributions. And according to the properties of Gaussian distributions, the variance of the X is the sum of the variance of these two components. For the first component, as I explained before, sigma r, we assume that it's proportional to a target width. It's a relative component. It shows to what degree you will follow the task, to what degree you will use the width of the content. Second component here, sigma a, it reflects the property of finger, the ambiguity. So it's a constant. It's independent from the task itself. So based on these assumptions, we can get this expression of how to calculate the standard deviation for the touch point distribution. And actually, this is a core conclusion from the Gaussian distribution model. It shows that the variance of the distribution is proportional to the squared width. So it has the variance of the distribution has a linear relationship to the squared width. This equation actually matches well of our daily experience. It shows that even if the target is very small, you will still observe some variance of touch points because there's the sigma a here. It basically tells you that the finger touch is ambiguous, and no matter how small the target is, you cannot really control your finger touch point to land your touch point inside that very small target. You always observe a certain amount of variance because of a sigma a. But if the width is very big, it means that the sigma a will play a smaller role here, so the variance will be largely determined by the width itself. So to test this hypothesis, we run a study. Participants perform a bunch of target selection tasks with various target size. It shows that it actually shows this linear relationship between the variance of touch points and the squared width. And we observe this intercept on the y-axis. That's the value of the sigma a square. it shows the ambiguity of finger touch. And we did a similar study for the in the y dimensions. So these two equations here also give us some estimations of alpha and sigma A here, and we can use them to further predict the variance of touch point distributions with the unknown target size. Okay, now, so I just described that we use this Dual Gaussian distribution model to predict the variance of touch point distribution based on target size. And with this very critical information, we can come back to our initial equation of predicting accuracy. Here we show that the standard deviation of touch point distribution could be expressed in this way. It's basically a function of the target width. And then we put in these values back to our equation here. We can estimate the accuracy of selecting a target based on the width of target only. So this is our model for predicting the accuracy of selecting one-dimensional target. You can see here the only variable here is just the width for target. And we also generalize this formula to the two-dimensional tasks. For two-dimensional tasks, the Gaussian distribution for the touch points follow a bivariant Gaussian distributions. And then, of course, and also the accuracy is the integral of this probability density functions over the area of a target. And we can also use the previously estimated sigma x and sigma y in the equation. So we can get the accuracy just based on the target area only. So now I just showed you how we derive the model based on some reasonable assumptions and follow mathematical principles. The next step, we run studies to evaluate these models. So we run study over 12 participants. They perform target acquisition tasks with different target size and shapes. Here we show the predicted accuracy versus observed accuracies for one-dimensional targets. The red bars are predicted values from our models, and the blue bars are observed success rate. You can see that for 4 millimeter and 7 millimeter targets, the prediction errors are less than 5%, and for the 2 millimeter targets, the prediction error is less than 10%. And we did a similar study for two-dimensional targets. In this case, it's circles. We observed the similar prediction error. And also, if we put the predicted error, so predicted accuracy, and observed accuracy in this two-dimensional plot, and we run linear regression over them, we observe a linear near unity slope and near zero intercept. It just shows that the predicted value matches the observed value very well. So we have a model, and we evaluate the results shows promising result. But what the models can do for us? The first thing is that we can use model to predict accuracy of selecting target for a wide range of target size. This figure shows how the accuracy increase when target size increase from very small to very, very large. And interestingly, the 48 dp one here, which is suggested by Android as the design guideline, shows that the target has pretty high accuracy. And also it shows that if you reduce the target size, it basically tells you how much performance degradation you will observe, and help designers to balance the size of target and the space they need. And also this model also shows that for circular target, you will have very high error rate or very low accuracy as the target size is reduced compared to vertical bar or horizontal bar. That's understandable or intuitive because for circular target, you have the touch point can fall outside the target from any directions. And the second application is about the keyboard implementation. So right now we have different size of a target, so different size of the devices, phones, tablet, or phablet. And also the keyboard can come in different shapes. Could be in regular QWERTY layout, or Nike layout, or one-handed layout. So the key size comes in different size. Our model can predict the accuracy of selecting each target And this information is very critical in designing keyboard decoder. Basically, a keyboard decoder is combine the probability from the touch signal to the signal from language model. And our model can be used to predict the spatial accuracy. And in fact, this model has been used to improve the Android 9K keyboard for pinyin input, and shows significant improvement over the previous approach, which just simply scaled up the regular QWERTY spatial model. So this is the conclusion of our research. Basically, we propose a model from some reasonable assumption and follow mathematical principles. The model can predict the accuracy of selecting target based on target size only, and also evaluate for both one-dimensional and two-dimensional tasks. And that's my presentation. I'm ready to take questions. Thank you.
Thank you, Xiaojun. Questions over here? Andy Wilson, Microsoft. So this is really nice. You showed the result for modeling the contact as a point. What if I have a shape? Is this now a triple Gaussian model, or do you have some other formulation?
So you mean if you use that contact area as a way to interact? Yeah, I think so. That means that, as I said before, that actually might just reduce the model to single Gaussian, because I said for the dual Gaussian, the first step is to model where you place the contact area. And the second model is to model how you reduce the contact area to a single point. So if you use the area to interact, it just means that we just don't need to do the second step.
So does that mean that some majority of the contact area has to overlap the target, or? I
think so. It depends on how the application will determine where target is selected. But I think actually we did some research about that. But currently I think the majority of the touch screen device is just use one single point. I think mostly maybe due to power consumption issues, other issues. So I think if we use the entire contact area to select targets, we will need to work out other way to determine whether target is selected. But I think the one reasonable assumption that we can just do integral, also get integral over the area to see whether the probability is over 50%.
Okay, one more quick question.
Hi, can you clarify how you used your result to improve the pinyin keyboard, the 9-key pinyin keyboard? Did you use it to change the size of the design of the keyboard?
So, okay, I can clarify a bit here. I think for example, for pinyin 9K keyboards has bigger keys than regular QWERTY layout. So previously, when have a QWERTY layout, you giving a location touch point, you estimate the probability of selecting a certain target, and you have assumption that what the Gaussian will be. But if you use the bigger keys, but how the Gaussian will change. So this model basically tells us how the standard deviation will change from a small key to large key, and then it will help you to determine the probability of selecting a key. Yeah.
Great, thank you for coming this session. Let's thanks all our speakers again.
Thank you.